Hello, welcome to this video on finding a basis for a subspace defined by the span of a set. So in this video, I'm going to explain the process. When we're given a set of vectors S. Remember that the span of a set of vectors, right? The span of S is a vector space. And what we're going to be doing is finding a basis for that span of S. All right. Now, recall from a previous video or from other readings, hopefully, I'm assuming you know what a basis of a vector space is. All right, it's a set of vectors that spans the space and is also a set of linearly independent vectors. All right, so let's get into it. So when I talk about the basis for the span, a basis for the span of a set, suppose we're given a set of vectors S. One, if S is a set of linearly independent vectors, right? That means that none of the vectors in S can be written as a linear combination of the other vectors in S. Then S would be a basis for the span of S, right? The vector space, the span of S, which is, remember, the span of a set is the collection of all linear combinations of the vectors in that set. Right. So if S is linearly independent, then S will be a basis for the span of S. On the other hand, if S is linearly dependent, then there's going to be some independent subset of S, right? So some smaller set of vectors in S that will be a basis for the span of S, right? And we'll figure out how to find those, right? How to shrink down S to an independent subset that would span the same vectors as S spans. All right. Okay. And so all I have for the rest of the video is just a bunch of examples where I'm doing this. Right. Now I'm going to be working in R2 and R3, right? You have two-dimensional and three-dimensional Euclidean space, because they can be visualized pretty easily. Now whatever I apply here, everything I do in this video, in these examples, can be applied to higher dimension Euclidean spaces, R4, R5, or even to general vector spaces, as I'll probably be showing you in a future video. Alright, so my first example, and these instructions I give here are the same instructions for every example. So suppose I'm given a set of vectors called S. What I'm asked to do is find a basis for the vector space, V equals the span of S. Right, and remember, the span of S is the set of all linear combinations of the vectors in S. Alright, so my first example, I'm in R2, right? All the vectors here are going to have two components. S equals just a set with one vector, 2, -3. And the span of S is the set of all linear combinations of 2, -3, but since it's only one vector, they'll call that a scalar multiple of 2, -3. So the span of this set is the set of all scalar multiples of 2, -3. Right, so 0, 0 would be in this, 2, -3 would be in this, 4, -6, 10, -15, any multiple, any scalar multiple of 2, -3 will be in this vector space, right, the span of S. So first I want to know is, because it would be nice if S were a basis for the span of S, right? So we'll check that first. So the first thing I'm going to ask myself is the set S a basis for the span of S? Remember, you have to check two things to determine if a set is a basis of a vector space. One, does S span the span of S. Well, yes, by definition it does, right? Every vector in here is a linear combination of vectors in S, right? As a scalar multiple of vectors in S. So by the definition of the span of S, clearly S spans the span of S. I mean, it's a little silly to say that, but it's true. Right? So I got that one. Then the next thing I check for, if I want to determine if S is a basis for the span of S, or for any vector space, is S a set of linearly independent vectors? Well, it's only got one non-zero vector, and if you've been watching my videos, I had a video on determining whether a set was linearly independent or dependent a while back. If a set has only one non-zero vector, then that set is linearly independent. Wonderful. And check on that. All right. So, like I said, because S is on the previous page, because S is a set of linearly independent vectors, right, then S is a basis for the span of S. All right. Now, this was a very short example, of course. They're going to get a little longer, a little more complicated as we go through the video. But I wanted to just refresh your memory, hopefully, as to how do we check for independence. Here I just said it's got one vector and is non-zero, so it's a linearly independent set. Remember that how we check for independence of a set of vectors. We look at a linear combination, which would be a scalar multiple here. So a1 times the vector 2, -3, and ask ourselves, when is this equal to the 0 vector? Right? And so we're looking for scalars a1 that would make this true. Right? And if this equation has only the trivial solution, right, where all the scalars, which in this case is just a1, when all the scalars are 0, right, that's called the trivial solution, because that's an obvious solution, right? If all the scalars were 0, if I put 0 times 2, -3, I'm going to get the 0 vector back. If that's the only solution, then the set was considered, linearly independent. And if there were other solutions, non-trivial solutions, where not all of the scalars were 0, then the set was linearly dependent. All right, well, remember how this equation here, where I set up a linear combination of my vectors in S equal to the 0 vector, that corresponds to a system of equations where the first components need to be equal, so 2 times a1 needs to be equal to 0, and the second components need to be equal to -3 times a1 needs to be equal to 0. And you can see from this that the value of a1 must be 0 and 0 only, right? So this equation has only the trivial solution. So what I said here earlier was, that S is linearly independent. That is true. But you could also, remember, when you have a system of equations, set up a little augmented matrix and put that into, reduced row echelon form or reduced echelon form. So here I have the coefficients of a1 and then equal sign bar and then zeros. And then, because when I'm checking for independence, this column on the right side of the bar is always going to be zeros, I can pretty much ignore it. Like, it's always going to be there. Right? This will always be zeros. No matter what row operations I perform, this column will remain a column of zeros. So very often, and sorry about the clutter here, instead of writing that last column of zeros, you just focus on the coefficient matrix, right? Which is just the matrix to the left of the bar. So we only need to focus on the coefficient matrix. I'll just say coefficients because I don't have a lot of room down here, sorry. And when I put that into reduced echelon form or reduced row echelon form, hopefully it's very clear here. That would just be simply a column with 1 0. And then you'd have this bar and then zeros on the other side. But again, I don't really care about that. That other side of the bar is always going to be zeros. And then I look at this and say, oh, well, that implies that A1 must be equal to 0. And 0 equals 0 would be fine. I can ignore that. That's always true. And I get only the trivial solution. Right? So, and every column has a pivot. Right? This is the pivot here, the lead one. And you see in this that every column, each column with a pivot will correspond to a vector from S that's in an independent set. Each column with a pivot corresponds to a vector in S that's in an independent set. So this was the first column, right? So then that means that this first column, right, this vector 2, -3, is an independent set itself, right? It's the only vector in there. So a lot of stuff, right? Again, lots of different ways we can see this. I know it's a lot of clutter here. First example, I'll do the first just couple examples, maybe a few of them where I go into more detail. But then I'll just refer to later. I'm just going to take this coefficient matrix, which you see is just made up of the vectors of S, right? The columns of the coefficient matrix are just the vectors of S. Putting that in the reduced row echelon form and determining if the vectors are independent, and if not, which vectors would form an independent set. Okay, so in this case, this example, S is a basis for its span, right? Obviously it spans because that's the definition of span, right? And it's linearly independent. So that means that every vector in here is a linear combination of the vector in S by definition, right? And the vectors in S are linearly independent, thus a basis. Okay. So next example, have the same instructions. Okay, I'm going to have the same instructions as this first example, where again I'm given a set of vectors called S. Right. So adjust this here. So here S is this set of two vectors from R2, 1, 5, -3, 7. And then find a basis for the vector space, which is just the span of S. Remember, the span of this set is the set of all linear combinations of those two vectors. So I have a scalar times 1, 5 plus some scalar, some real number times -3, 7. Right? And A1 and A2 are real numbers. Right, so you could let A1 and A2 be any real number you want and get a vector from the span of S. And it is a vector space. Now the question again is, I'll start off with, is S a basis for the span of S? All right. Now again, I don't need to check that first, the first statement about the, what does S span the span of S? Yes, by definition it does. Right? S spans the span of S clearly. All right, because every by definition every vector in here is a linear combination of the vectors in S. So yes, S spans the span of S. So the only one I really need to check is, are the set of vectors in S linearly independent? All right, now again, in a video I've put up before when we checked for independence, if a set of vectors has only two vectors and they're not scalar multiples of one another, which these are not, I can't multiply this 1, 5 by any scalar to give me negative 3, 7, and vice versa. So I have two vectors that are not scalar multiples. And remember that was a little quick shortcut there. If you have a set of two vectors that are not scalar multiples, then that set of vectors is linearly independent. One is not a linear combination or a scalar multiple of the other. So check on that. So noting both of these things, S is indeed a basis for the span of S. Okay. Now you could have also done this, right, to check for independence. You say, or you take a linear combination, of these two vectors in S, a1 times 1, 5 plus, say a1 times 1, 5 plus a2 times negative 3, 7, and ask, are there values of a1 and a2 other than 0 and 0 that would give me the 0 vector? All right, and then, as I mentioned before, this kind of equation sets up a system where you could write the system out, but I'm just going to write the augmented matrix for that system with 1, 5 down the first column, write the coefficients of a1, which is just the first vector from S, and then the coefficients of a2 down the second column, the negative 3 and 7, which is just the other vector in S. Then you have a bar, and then again the zeros here. And really I don't need to worry about the zeros. Those will always be there when I perform row operations. And then I put I'm just going to focus on the coefficient matrix that's made up of the vectors from S and put that in reduced row echelon form. And hopefully you can tell that if I do operations, I'll do one on a calculator later, the TI-84 Plus that I've got on the screen. But this is just going to be 1, 0, 0, 1, the identity matrix, and then you have zeros over here. But again, I don't really care about the zeros. That's always going to be zeros when I'm checking for independence. So we'd have a1 equals 0, a2 equals 0. Only the trivial solution is a solution to this equation. So indeed, the vectors in S are linearly independent. All right. You can also say too, hey, look at the coefficient matrix in reduced echelon form. The first column is a pivot column, right? Has one of these leading ones. So this vector, right, 1, 5, and the second column is also a pivot column, has one of these leading ones in reduced echelon form. So the second vector, the second column of the coefficient matrix, negative 3, 7, these vectors would form an independent set, which is all of set S, right? So set S is linearly independent. Wonderful. Okay, now I forgot to do something in the first example. So if you bear with me, I wanted to, again, I mentioned that the reason I'm doing R2 and R3 is so that we can visualize things, on the two-dimensional coordinate plane or three-dimensional space. So I'll come back to this, right? We'll come back to this, but I wanted to talk about example 1 again real quick and show you a picture in 2 dimensions of what's going on here. So I'm going to go to a website here. This is geogebra.org, and they have a 2-dimensional calculator and 3-dimensional calculator. And right now I've got the XY plane or X1, X2 plane, and the origin is labeled A. And here was the vector from the first example, right? The vector in S, right? 2, -3. There it is here, right? As a position vector, 2 to the right, 3 down, 2, -3, that motion. And the span, right? Now I've talked about this in other videos, right? The span of this vector, remember, is any linear combination of this vector or any scalar multiple of this vector. And if you multiplied this by any scalar, you'd get vectors that traced out a line, right? This line here, this green line. Every vector that's a multiple of v1 would end at some point on this green line, right? And yeah, so hopefully you can see that the v1 then would be a basis for the green line, right? Every vector on the green line is a multiple of v1, and v1 is just a single vector, so it doesn't depend on anything else. It is independent, right? So that was it. That's all I wanted to show for example 1, and something I wanted to write as well on the pages was this, that the span of a single vector forms a line. This corresponds to a line containing the origin, and this is in R2, right? But I'll just say a line containing the origin and just know that we're in R2, right? So the span of a single vector forms a line. Now the span of 2 vectors that are independent, right, like on the second example, the span of 2 vectors that are independent, you'll see form a plane. Right? Now I'm not going to, it doesn't color in the entire plane here, so I'll show you. Here is the second example's vectors from S. We had 1, 5 and -3, 7, and I'll back this up so we can see the whole thing. There we go. 1, 5, this is the red vector, and -3, 7 is the green vector. Now do you see how they're not on the same line, right? They don't point in the same direction or opposite directions. So when you look at the span, you're not getting a line, but you'd get the entire plane. It bumps it up 1 dimension, right? And think about that, since these are going in different directions, you could take any amount of v2 plus any amount of v3 and go anywhere on the entire plane. All right. So, and you need 2 independent vectors to make a plane. Right? When you look at the span of 2 independent vectors, you get a plane. All right. So this is a plane. All right. So again, the span of 2 independent vectors is a plane containing the origin. Right? And since this plane is the entirety of R2, right? All of R2 is a plane. The span of S is just R2. So what we have here is that this set of vectors is a basis for R2, right? Since the span of S is R2. And I've talked about that in other videos before too, where if you have a set of vectors from R2 and they're 2 independent vectors, remember every basis for R2 has 2 vectors. If you have a set of 2 independent vectors from R2, that will be a basis for the entire space R2. Great. But the key thing I want to point out here, though, is this. The span of 2 independent vectors is a plane, or like a flat sheet, containing the origin for that space. Okay. So another example, where again I'm doing the same stuff, All right, I'm given here's a set of vectors called S, and then I show you what the span of S looks like. So S has the two vectors 5, -2 and 15, -6. Then the span of S is, all linear combinations of those two vectors, right? Some scalar a1 times 5, -2 plus some scalar a2 times 15, -6. Right? A1 and a2 are scalar, are real numbers. Right. So again, the question is S a basis for the span of S? All right. So again, the first one's obvious. S does span the span of S, right? I do not need to check that because by definition of the span, every vector in this, the span of S, is a linear combination of the vectors of S. So S spans the span of S. Now, is S linearly independent or linearly dependent? All right, so this time I have two vectors, but they are scalar multiples of one another. Right? If I were to take 5, -2 and multiply it by the scalar 3, I would get 15, -6. So these are two vectors that are scalar multiples. All right, so that means that this set of vectors is linearly dependent. S is linearly dependent. Uh-oh. That's no good. All right, so the answer to this question here is no. S is not a basis for the span of S. So we have to find one. All right. So since S is not a basis, it means we're going to have to find a subset of S. All right, so some smaller collection of vectors in S. Now this has two vectors, so a subset of S could be the two vectors, but I've already looked at them, or just this vector with the set with 5, -2, or just the set with 15, -6, or the set with no vectors, but you're not going to come across too many vectors unless you're talking about empty space. You're not going to come across vector spaces with no vectors as a basis. So since S is not a basis for the span of S, we're going to be finding a subset of S that is a basis for the span of S. Oops, span of S, not the span of 2. All right, so how do we do this? All right, again, a couple ways. I'll show you like a longer way first. And you'll see that the shorter way, it just boils down to, again, taking the vectors of S and forming a matrix, and what would be the coefficient matrix of a system, and putting that in reduced row echelon form, and going from there, looking for pivot columns. But how do I find a subset of S, though, that is a basis for the span of S? So remember when we're checking S, when checking S for independence, we set up this equation. When checking S for independence, you set up the equation. So you took when is a linear combination of the vectors in S equal to the zero vector? So a1, some scalar times 5, -2, plus, and then some scalar a2 times 15, -6, when is this equal to the 0 vector? All right. And then I'll do the thing with the corresponding system. All right, 5, -2, 15, -6, 0, 0. Has, again, you don't really need to have the zeros over here because it's always going to be 0. And then I'll put this into reduced echelon form, or reduced row echelon form, RREF, which will look like on your calculator. And again, I could perform some operations here, do it by hand, but this is where I want to start going to the calculator just to save on some writing, save on some time. So again, what I'm showing you here is from the TI 84 Plus, and it's similar to the 83 if you've got one. Second, go to the matrix where it says matrix menu there, over to edit. And once I go into matrix A, I enter this has now again I know that these are going to be zeros, so I'm just going to work with the 2 by 2 matrix. All right. So I'm going to just enter a 2 by 2 matrix here, where the first row is 5, 15, has entries of 5 and 15. Second row has entries -2, -6. All right, and then I'm going to put this, get out of here, go quit, go back to the main calculation screen, go back to the matrix, over to the math area with the cursor, scroll down or scroll up until you hit RREF. And don't confuse it with REF, please. That's just plain old row echelon form, or just plain old echelon form. I want reduced row echelon form. So I put RREF, and then what matrix do I want to put in that? Go back to the matrix, and then under names, this 2 by 2 matrix that we had. All right. So this would be, if I put it in reduced echelon form, 1, 3, 0 again on the other side, and then 0, 0, 0. All right. So we have here 0 equals 0 from the second row, right? Which is fine. It's totally true. See, only the first column is a pivot column, has that one of those leading ones. So A1, when I'm solving for A1 and A2 in this equation, A1 would be considered a basic variable, right? Because that first column with the coefficients of A1 has a pivot. And A2, the second column that correspond to coefficients of A2, that doesn't have a pivot. So A2 is what they call a free variable, right? Meaning it can take on any value you want, any real number value you want. Now, very often people leave it as A2, but I like to personally replace my free variables with other expressions, right? So I'm going to let A2 be replaced by the letter T, okay, where T is just some number. Again, it could be T, S, R, 5T, a third T, T plus 1. It can be any expression that takes on any real number value, right, where T is any real number. Okay, so then from this matrix here, the first row is telling me that A1 plus 3A2, so plus 3T, is equal to 0. So A1 equals -3T, right? And we said that A2 is the value of T. So you see how this has infinitely many solutions, right? I just this equation up here, where what linear combinations of these two vectors give me the 0 vector, has infinitely many solutions. You just pick say when T equals 1, or T equals 100, or T equals 5,000, or whatever, right? Not just 0 and 0. So because it has infinitely many solutions, we definitely know that S is linearly dependent. Right. So since S is linearly dependent, that means we can remove some vectors, right, to try to get an independent set. Right. That means that one of the vectors in S can be written as a linear combination of the others. So how do I determine that? Which vectors in S are linear combinations of others? Well, just use a non-trivial solution to this equation. So for here, I'm going to let the value of t just simply be 1. If I let t be 1, Then the value of a1 would be -3, and the value of a2 would be 1. And popping those into my equation when I was checking for dependence, I get this here. -3 times the vector 5, -2 from S, plus, and then a2 is 1, so plus just, 15, -6 will be equal to the 0 vector. All right, and then any vector that has a non-zero coefficient, which both of them do, -3 and 1, has any vector with a non-zero weight, can be solved for. You can express that vector as a linear combination of the other vectors. So what I'm going to do is I'm going to take this one here because the coefficient of it is 1. It'd be easy to solve for. I'm going to solve for this vector. And that would be simply done by just leaving it on the left side. So the 15, -6. And then just, adding this to the other side. I have -3 times 5, -2 there. I would just add it to the other side. And having the 0 vector over here doesn't affect anything. So I'd have +3 times 5, -2. And I said that at the very beginning, right, that the second vector in S was just 3 times the first vector. And we're seeing that relationship right now. All right. So because 15, -6, right, because 15, -6 is a scalar multiple of 5, -2, well, that means we don't need 15, -6. We only need 5, -2 in our set of vectors. So from this little line here, that tells me I can remove, or we can remove the vector 15, -6 from S. All right, I'll go to the next page here, and that would create a new set of vectors, which I'll call S prime. So that creates this set, which again I'll call S prime. And if I take out the 15, -6, all I have left is the vector 5, -2. All right, and this should now, and then the question becomes, is this a basis for the span of S? Right? Is S prime a basis for the span of S? Right? Now be careful here. Right? One's S prime. Right? S is the set of the 2 vectors I started with. S prime is this set with 1 vector. All right. So remember the questions. Does S prime span the span of S? Now this one isn't as obvious. All right. But it will be, okay? It will, but this one isn't as obvious because this is not S, right? This is S prime. So another question, the same question would be: is the span of S prime equal to the span of S? Right. So remember the span of S. The span of S has linear combinations of the vectors of S. So, in the span of S, we have these vectors. Some constant, some scalar times the vector 5, -2, plus some scalar times the vector 15, -6. All right, and then here's where this relationship comes in that we found earlier. Remember, 15, -6 is a scalar multiple of 5, -2. So this is equal to some scalar times 5, -2. Scroll this up. Plus, and then 15, -6. I'm going to replace with 3 times 5, -2. So I'd have 3a2 times 5, -2 for that second term, right? And then notice now that both of these terms have the vector 5, -2. You can factor that out, and you'd have the scalar a1 plus 3a2 times the vector 5, -2. All right. So can you see from this line of reasoning that every scalar, every linear combination of 5, -2 and 15, -6 is just the same as a scalar multiple of 5, -2. And this vector would be in the span of S prime, right? Because the span of S prime, right? S prime is just the vector 5, -2. Is the span of S prime is made up only of multiples of 5, -2. And what we're seeing here is that every vector in the span of S is also a vector in the span of S prime. So the answer to this question is yes. Sorry, yes. All right. This is true. The span of this one vector is equal to that span of the two vectors we started with. Okay, and then finally, is S prime linearly independent? Or let's say independent. And as we saw in my very first example, S prime has one non-zero vector in it, so it's independent. So the answer is yes. So after all that, we can just very simply now say that set, right, S prime. So S prime equals just the set with vector 5, -2 in it is a basis for the span of our original set, right, the span of S. Okay. And I didn't have to use just 5, -2. I could have used 15, -6. Right? We could have instead here we could have said that 5, -2 is 1/3 of 15, -6, and then removed 5, -2 and gotten the same thing. But just remember that bases are not unique. Right? Just because I say this is this is a basis for the span of S, it's not the basis. Right? There are others. Like I said, like basically any multiple of this would also be a basis. Again, the shorter way to do this, right, that was pretty long there, setting up all those equations and whatnot. The much shorter way to do this would be to look at, here's back the start of the example, and I'm asked, is this set a basis for the span of the set? Yeah, the much shorter way to do it would be to look at the reduced row echelon form. Right? Remember, I formed a system and all that, and these columns will just make up the columns of the coefficient matrix. Put it in reduced row echelon form, and then where are the pivot columns, basically? All right. The first column is a pivot column, so that'll correspond to a vector from S that'll form vectors from S that'll form an independent set. So I could have just done this and said, the set with vector 5, -2 will be an independent set, and it also spans the span of S. So there's my basis for the span of S, the set with vector. A basis would be the set with the vector 5, -2 in it. All right, so you just look for pivot columns in reduced row echelon form, and that's what I'm going to do from here on out. All right, for the rest of the examples, just to speed things up a bit. All right, so the next example again. Oh yeah, sorry. So absent-minded sometimes. I also wanted to show you a picture. All right, look at this on the coordinate plane R2. All right, so we have 5, -2, 15, -6. Let me go to the GeoGebra site and get rid of these guys. And now we're on this example where my vectors in S are 5, -2 and 15, -6. And do you see how they fall on the same line? They point in the same direction. They are on the same line. So the span of one will be equal. The span of both of these is equal to just the span of one of them. Right, and let me just get rid of these two now. Get rid of that. The span of this vector will be this line. Right? Remember the span. I said that in the beginning. The span of a single vector is a line containing the origin. So the span of the red vector is this line. But you see how it's also the span of the green vector, right? So it's definitely the span of both of these. And can you see how one of them is unnecessary, right? So I wouldn't need 15, -6, say, and then 5, -2 would be enough so that the span is equal to this line, right? So that's what I did on paper earlier, right? As I figured out that I don't need both of them to form the span of the set of the two vectors. I just need the one vector, right? 5, -2, or 15, -6, right? Both of them have an equal span. Both of them would form that line when I span them. Okay, let's get down, get rid of that, and go back to the worksheet. All right, so now for my next example, again, still in R2, all right, but now we'll speed things up a tad. Okay, I have a set of, here are 3 vectors from S, from R2. Right, they all have 2 components. 2, 3, -4, 8, and 10, 15. And the span of this set would be, again, any linear combination of these 3 vectors. So a scalar times 2, 3, plus a scalar times -4, 8, plus a scalar times 10, 15. All right. And the question again is, and I'll start off with, is S a basis for the span of S? All right, now again, obviously the first one's fine. Right, the first, the S by definition spans the span of S, right? So I don't need to check that. All right, by definition, every vector in the span of S is a linear combination of the vectors of S. Now, is it linearly independent or linearly dependent? Again, in a prior video I've put up, if you've seen it, about independence and dependence, there was another shortcut thing here. If the number of vectors in the set is greater than the number of components of each vector, then the set will be dependent. All right. So for instance here, this has 3 vectors, and each vector has only 2 components. So S is going to be a dependent set, and that's bad, right? Yeah. So this tells me that S is not a basis for the span of S, right? For that vector space, the span of S. So let's find one. All right. So again, what you could do is try to figure out, find one, figure out how one vector can be written as a linear combination of the other 2, and then that means you only need those other 2, and then not the one vector, and remove it, and then you start over again and say, hey, now of these 2 vectors, are these 2 vectors independent? And if they're not, then you can remove another one, and if they are, you're good. Again, you can go through all that crazy thing with the equations that I set up, where you set a linear combination of the vectors equal to the 0 vector, and then you figure out relationships, what vectors are dependent on what other vectors, and so on. But again, I'm just going to jump to the quick here. So we're going to find a basis for the span of S, now that I know that S is not a basis. So if I were to set up that equation, right, where I take a linear combination of these 3 vectors and set it equal to 0 vector, it would have this matrix when I set it up as an augmented matrix. Now again, I'm not going to worry about that last column of zeros to the right of the bar. So I'm going to stop right before the bar where the equal sign should be. And the coefficient matrix will just be made up of the vectors of S. I'll have 2, 3, -4, 8, and 10, 15. And there'd be this bar here and then some zeros. And what I'm going to do is put this into reduce row echelon form. Again, with the aid of my calculator here, just to save on writing and maybe save a little time for the video. Alright, so here, come on, turn on. Alright, so back to the matrix menu. I'm going to edit matrix. I'll just keep editing matrix A, and this time I have a 2 by 3, right? 2 rows, 3 columns. And I'm entering the first row is 2, -4, 10. Then 3, 8, 15 for the second row. And get out of here, quit. Now, since the last entry I made was already reduced row echelon form, I can just go second and then enter, and the last entry will show up, and I just enter again. There it is. Alright, so putting this in reduced row echelon form, I'm getting 1, 0, 0, 1, 5, 0 for the columns now, and then again there'll be this bar here. So you see, if I set up a kind of equation, the variable a1 would be basic, the variable a2 would be basic because those are pivot columns, and then the variable a3 would be free. And each pivot column just corresponds to a set of a vector that'll be in an independent set. All right, so this first pivot column corresponds to the vector 2, 3. Second pivot column corresponds to the vector -4, 8. And there you go. This set of vectors will be a basis for the span of S. And it's really that quick and simple. Hopefully, after you've understood everything, all the lawn way stuff I did before on the previous examples. All right. So let's call this S prime equals the set with vector 2, 3, and the set with vector -4, 8. Right. And what this means is, this means that you can express 10, 15 as a linear combination of these two. So if I could do that, that means I could replace, if I take a vector from the span of S, it's some scalar times 2, 3 plus some scalar times -4, 8, pardon me, plus some scalar times 10, 15. I could then replace the 10, 15 with a linear combination of these two, and then the whole thing, all the vectors in the span of S, would just be linear combinations of these two vectors. You'd only have the vectors 2, 3, and -4, 8 left, and then the 10, 15 would disappear, be replaced. All right, so we're seeing that the span of S is equal to the span of S prime. So that's good. And as I said before, you'll notice, that again, these pivot columns will correspond to a set of vectors that will be independent, and S prime is linearly independent. All right, and you can double check if you want by setting up that equation or looking at them. There's only, again, 2 vectors here, and these are 2 vectors that are not scalar multiples of each other. So the set S prime is independent. So both of those are good, and so S prime is this set of 2 vectors is a basis for the span of S. Right. The span of that set of vectors that we start with. And you could also say span of S prime. We said that the span of S is equal to the span of S prime, right? S prime does span the same set that S does. And then now for some visualization here. Right, again, these are vectors from R2, so I can put some pictures up for you. Let's take a look. All right, so it was these vectors here. Right, so I had vector 2, 3 was an S, right, that red arrow. Vector -4, 8 was an S, that green arrow, and then vector 10, 15. Let me back this up a bit, and then vector 10, 15. Now do you notice how vector 10, 15 is just a scalar multiple of V6? Vector 2, 3, right? It's just vector 10, 15 is just 5 times the vector 2, 3. So they point in the same direction. So what does that tell me? That tells me that one of those vectors is not needed, right? So let's just, so I don't need to have 10, 15 when I talk about the span of these 2 vectors. Now these 2 vectors, 2, 3, and -4, 8, these do not point in the same direction. So these are both needed. And then the span of these two, remember the span of two independent vectors forms the plane. So the span of all three of these vectors that I started with is actually all of R2, the entire plane. And because this vector is just a scalar multiple, or a linear combination of these two, it's actually only a scalar multiple of the first one, I don't need it. And I create the same span. The span of these two vectors, the red and the green, is the same as the span of these three vectors. And then these two would form a basis for that same set. Okay? All right. Next example. All right, so I have one more example here where I'm in R2. All right, so I'll be going to the two-dimensional GeoGebra page, and then we'll get into some examples in R3. All right, so R2, some R2 vectors again. Here I have the set of three vectors: -1, 1, -2, -3, 6, 7, -14. And you may notice already that this vector is just -3 times the first one, and this vector is just 7 times the first one. So both of these are just multiples of this one. So it looks like the only one I need is this one. All right? I really only need one of these vectors, and we're going to see that as we go through the process. Right? And then the span of S, right, again, is just all linear combinations of the vectors in S, right? So some scalar times 1, -2, plus some scalar times -3, 6, plus some scalar times 7, -14. Okay. So again, the question is, is S a basis for the span of S? I'll tell you right now, S is a linearly dependent set, all right, for the same reason as the last example. All right, linearly deep. Just know that the word linearly should be in here too, right? Because the number of vectors is greater than the number of components each vector has. Right? So it's going to be dependent. It means that S is not a basis for the span of S. But what is? All right, so again, if I were to check for independence, I would take a linear combination of these three, set it equal to the 0 vector, and try solving, and that would correspond to a system with this matrix, right, where the coefficient matrix would just be, again, these vectors would be the columns, 1, -2, -3, 6, and 7, -14. Need to have a bar and some zeros on the other side, but again, I don't really, those will always be zeros, I don't need those. And then put this in reduced row echelon form, which don't need to go to the calculator for this one, because all I would need to do is take the first row, multiply it by 2, and then add it to the second row, and then the second row would be all zeros, and you got 0 equals 0, and then the first row, I'd have the 1, -3, and 7. All right. So you see, like I said earlier, we're only going to need one of these vectors to form a basis for the span of S, right? Only the first column has a pivot, has one of these leading ones when we're in reduced echelon form. So that corresponds to this first vector of S, right? And there'd be two free variables, right? So meaning that each of these two vectors can be written as a linear combination of this one, right? Or just a scalar multiple of this one. So S prime is just the vector 1, -2. And what you're going to see is that the span of S prime, the span of this one vector, is equal to the span of S. Right? Because if you look at S, the span of S has linear combinations of 1, -2, 3, -3, 6, and 7, -14. But I can take each of these two, 3, -3, 6 is just -3 times that, times 1, -2. So I can write this in terms of 1, -2. And 7, -14 is just 7 times this vector, so I could replace this with something with 1, -2 in it. And then I get this linear combination of these three is really just equivalent to a scalar multiple of this one. All right, so the span of S is equivalent to the span of this one vector. and it's just a single vector. And I already told you, right, when you know, this, again, the shortcut thing, when you put that coefficient matrix in reduced row echelon form, the pivot columns will correspond to a set that is independent, right? But you can see it's a single non-zero vector, so you know, S prime is linearly independent. So both things are good, both things are happening, meaning that S prime is a basis for the span of S. Right. And then what would it look like? All right, I can go to the calculator, go to the computer website, GeoGebra, but you can tell me already. The span of this set of vectors is equal to the span of one vector. And remember, the span of one non-zero vector was a line through the origin. All right, well, let me show you. All right, so this example had these vectors in S, right? There's 1, -2, that little blue arrow that just showed up, -3, 6. See how that's on the same line there? Points in, you know, it's pointing in the opposite direction, but they're in line with each other. And then 7, -14, look at that. They're all on the same line. So that means that only one of these is necessary, right? In order to form that vector space, the span of this vector will be equal to the span of these two because they're on the same line, and it'll be equal to the span of these three because they're all on the same line, right? And because they're all on the same line, you know, only one of them is necessary, only the vector 1, -2, or you could have chosen -3, 6, or you could have chosen 7, -14. Remember, a basis is not unique, but I'm just going to stick with the convention that, you know, a pivot column in reduced row echelon form will correspond to a vector, the set of vectors that I use. Okay, wonderful. All right, now that's the last example from R2 that I have for you. Now I'm going to go into R3. All right, and again, hopefully these go a little faster. All right, so here I have a set of vectors in R3, and it's only a set with one vector in it. And the span of S is just, again, all the multiples, all the scalar multiples of that vector, 1, 0, -4. And remember, I've been saying this, you know, that when you look at the span of a single non-zero vector, this will correspond to a line containing the origin, but this time it's a line in 3D, right, in R3. So the question I'll start with, you know, is S a basis? Well, you know, S, again, I'm not gonna write this time. I'm just gonna say it. S definitely spans the span of S, right? By definition. S is also linearly independent, right? It's a single non-zero vector. So S is a basis for the span of S. Right? Every vector in the span of S can be written as a linear combination of the vectors of S, and S is linearly independent. So that's all I need. All right? Very quick and simple. And when I go to show you how this is pictured, I'm going to have to go to the 3D calculator this time. So again, here's 3 dimensions. You have a green axis, a red axis, and a blue axis, kind of like an X, Y, Z, or X1, X2, X3 axes if you want. And then, you know, the origin is labeled. I got point A there where the blue dot is. Here's the vector from S. You know, and let me scroll there. There it is, pointing down there. Right? Right? There's that red vector, 1, 0, -4. And, you know, the span is going to contain any multiple of this. Remember, a multiple of a vector is just going to point in the same direction or opposite direction on the same line. Right? So here's the line that's representing the span of that vector, this blue line. And you can see that very clearly that red vector falls on that line. All right, hopefully it's clear when I swirl this around a bit. Oops, something's not good. It's really hesitating on me. Right, but you see that red vector is clearly on this blue line, and every multiple of the red vector will be on this blue line. All right. So that one vector is the only vector I need to create that span, right? To create the span of that one vector is that vector space represented by that line. So that single vector is a basis for that vector space. Great. All right. Next example. And just some vectors here from R3, right, with 3 components. So S equals this set with 2 vectors from R3. You got 2, 3, 5, and -4, -6, 10. Now the question I'll start, and then the span of S, right, would be again all linear combinations of those two, right? A scalar times the first plus a scalar times the second, any vector that looks like that. And the question is S a basis for the span of S? And hopefully you can see that the answer is no. S is linearly dependent. Right? When there are 2 vectors, it's very easy. Right? Isn't this second vector just -2 times the first vector, right? They are scalar multiples of each other. And when you have a set of 2 vectors that are scalar multiples, that set of vectors is linearly dependent. So S is not a basis. So that means I have to go and find one. It is not a basis for the span of S. Right? But I already mentioned earlier that I can say that this vector is just a scalar multiple of 2, 3, 5. So I don't need this one, right? I don't need -4, -6, 10. I can replace -4, -6, 10 with -2 times 2, 3, 5, and then write everything in terms of just the vector 2, 3, 5. So S prime with just the vector 2, 3, 5 in it. This would be a basis for the span of, for this set here, the span of S. Right. Now again, you could have set up a matrix, right? A 3 row by 2 column matrix with these. Put it in reduced row echelon form. And on the calculator, if there are more rows than columns, you just have to add some columns of zeros to make the columns and row numbers equal, and then just ignore those zeros when you put it in reduced row echelon form. So you can use the calculator if you want to, or by hand, put it in reduced row echelon form, and what you'll notice is that only the first column would have been a pivot column, so only this first vector was necessary for a basis. All right, let's visualize this. All right. So the span of these 2 vectors, right, we said was equal to the span of this vector, right? And as I said in the last example, right, the span of one vector, one non-zero vector, is a line containing the origin. But this will be in 3 dimensions, right? So let's see that. Let's see that this creates a line going through the origin again. All right, so let me take these out. All right, so remember my set S this time had 2, 3, 5. There it is, right, that red vector. And then -4, -6, -10. Now, it may not be clear. I mean, you can tell, hopefully, that these are on the same line, right? If I can line them up perfectly if I wish, like that. Hopefully, it's obvious that these are on the same line. So that just means they're scalar multiples of one another. Let me go back to the home view. Standard view. All right, there we go. And then look, here's that line, right? In blue. You see the blue vector and the green vector are on this blue line here. That blue line represents the span of these vectors, right? Any linear combination of these red and green vectors are going to fall on this line, but you see how one of them is not necessary, right? I can just use the red vector to form that line, or I could just use the green vector, -4, -6, 10 to form that line. But just know that both of them aren't necessary. We can eliminate one of them, so that's why I eliminated -4, -6, 10, and said that 2, 3, 5 was a basis for this vector space, right? The vector space that forms this line. Great. All right, next example. Again, just some vectors from R3 again, three-dimensional space. This time again, I have two vectors. 0, 1, -1, 4, 2, -3. Then the span of this set of vectors is, a scalar times the first plus a scalar times the second, every linear combination of these two. Hopefully you see that, obviously S spans this, so that's one check. And then I mentioned this before, when there are two vectors that are not scalar multiples of each other, those vectors are independent. And you can see I can't multiply these by scalars to get one another. So they're not dependent, they're independent. So S is a basis. I need them both for the span of S. All right, and let's see what this would look like. Remember what I said earlier, how the span of two, this is way back in like the second example from this video about an hour ago. Remember the span of two independent vectors formed a plane, right? The span of one vector formed a line through the origin. The span of two independent vectors will form a plane containing the origin. All right, but this will be in 3D here. And I'll show you what I mean on the GeoGebra site. All right, so get rid of that. Go back to the standard view here. All right, so this time S had 0, 1, -1, which you're seeing is pointing downward over there. I'll scroll around to see it a little bit better later. And then 4, 2, -3 is just pointing down that way. See how these are not on the same line? All right, these are independent vectors. These do not fall on the same line. And when you have that, when you have two independent vectors, the span of those will form a plane. Right? There's a sheet there. You see this sheet? Every vector that is a linear combination of the red and the green will fall on this sheet. Right? This plane. Hopefully you can see. Right? When I make a thin blue line, right? All those, the red and the green, definitely fall on this blue sheet. Right? And I need them both, right? If I got rid of one of them, right? If I got rid of the green, then I'd have one vector, and the span of one vector is a line, not a plane. So I need them both to be able to create this plane when I look at the span of the two vectors. So those two vectors are indeed a basis for the plane, right? A basis for the span. All right. Here's another one. So another set. Now this time I have a set of three vectors. All right, a set of three vectors from R3, and I'm asking the same thing. Is this set of vectors a basis for the span? Now it spans it. Now I need to know if they're independent. All right. Now there's not just two of them. There's not just one of them. So I have to do that check with the equation where I set a linear combination of these equal to the 0 vector, and then figure out if it has just a trivial solution or more than just a trivial solution. Well, that'll correspond to creating this matrix, right? When I set up that system, I'd have the first column would be the first vector, the second column the second vector, third column the third vector, and then I'd have a row and then a column of zeros. But I don't care about that, right? I just know there's going to be zeros over here all the time when I'm checking for independence. I put this into reduced row echelon form, this matrix. Now this is, I could do it by hand, but again, just to save some time, save some writing, I'm going to go on the calculator. So I go to the matrix menu, over to edit, make a matrix A, make a 3 by 3, right? This is a 3 by 3 with these numbers. First row, 1, -1, 0. Second row, 3, 1, 4. Third row, 1, 2, 0. All right, and the last one's already a 0. All right, then I get out of there, and I've already, the last entry was reduced to echelon form, so I'm just going to do it again. All right, here it is, and that's the 3 by 3 identity matrix. All right, so like if I were setting up that equation, the first scalar would be 0, the second scalar would be 0, the third scalar would be 0. So only the trivial solution would be a solution to that equation where I set up a linear combination equal to the 0 vector. So this set is linearly independent. Or you could also say, hey, each column, the first, second, and third column have a pivot. So this first, second, and third vector form an independent set. So S is a basis for the span of S this time. All right, and now we've talked about what the span of a single vector is, right? That's a line through the origin. The span of two independent vectors was a plane through the origin, just increases in dimension, right? Instead of a single, one-dimensional line, it's a two-dimensional plane, a sheet. The span of three independent vectors is basically all of 3D space, right? All of three-dimensional space. This is actually equal to R3. Right? Every vector in R3 should be able to be written as a linear combination of these three vectors. And let me show you again some pictures. Right? So again, these vectors from S this time were 1, 3, 1. Let me go back to the home view. Right, so there's 1, 3, 1, negative 1, 1, 2, and 0, 4, 0. And you see, let me zoom in a bit. You see how these three vectors all point in different directions, right? They're not all on the same plane either. Like these two are on the same plane, the red and the green, I can line those up. But the blue is not on that plane, right? Blue is pointing in a different direction. The blue and the red are on the same, any two vectors can form a plane, right? The span of any two independent vectors form a plane. The blue and the red would be on the same plane, but not the green. You see how the green is pointing in a different direction. And the same thing for the green and the blue, right? The green and the blue, I can make a plane that goes through those, but then, the red, I can line those up. Then the red points in a different direction. So all three of these are non-coplanar, right? They point in all three different directions, right? And since all three of them point in different directions, I need all three of them for the span, right? I can't just get rid of one of them. If I get rid of one of them, then the span will be a plane and not in the entirety of 3D space, right? So if I got rid of the red vector, I'd get the plane with the green and the blue on it. But then, where's all the stuff in the direction of the red vector? I don't have those. So I need the red vector. If I get rid of the blue vector, I'd have just the plane, spanned by the red and the green. But what about all the ones in the direction of the blue, or that I need the blue vector for? I need the blue. I need all three of them, right? So all three vectors form a basis for the span of those three vectors, right? And the span would be all of 3D space, right? And that's the case for the span of any set of three independent vectors form a three-dimensional space, right? Just like the span of two independent vectors form a two-dimensional space, a plane. And the span of one independent vector, one vector, forms a one-dimensional space, or a line. All right. So I just got two more. Bear with me here. I know this is a while. Right. So here, S equals this set of three vectors: 2, negative 1, 0, 0, 2, negative 1, 6, negative 5, 1. The span of S is made up of all linear combinations of those three. And the question I'll start with is, again, is S a basis for the span of S? All right. So obviously S spans the span of S, right, by definition. So we're checking for independence now. And again, you set up that equation where I take a linear combination, set it equal to the 0 vector. And the corresponding matrix, coefficient matrix would be 2, negative 1, 0, and then 0, 2, 1, negative 1, and then 6, negative 5, 1. And then you'd have, some zeros on the other side. And I'd put this into, I'll do it below it, right, so we can see the correspondences here. I'll put this into reduced row echelon form, RREF. All right, and again, I'm going to do this on the calculator. All right. So go to the matrix menu, over to edit. It's another 3 by 3 here, right? These numbers 3 by 3. So I keep the size. The first row is 206. Second row, negative 1, 2, negative 5. Third row, 0, negative 1, and 1. Alright, and then get out of here, and I've already got the reduced row echelon form put up as my last entry, so I'll just re-enter that. And look at this, right? So putting this below, you'd have, you got 1, 0, 0 for the first column, 0, 1, 0, and 3, negative 1, 0, and then a bar. And then again, there'd be zeros on the other side when you're checking for independence. So you see how there'd be a free variable, that the third scalar. So that means that that third vector really isn't necessary. I should be able to write this vector as a linear combination of these two. And really you can see that if I take 3 of the first vector and then subtract the second vector, I would get the third vector. So the third vector is not necessary, but the first two are, right? The first two columns are pivot columns, have one of these leading ones in it. So this vector, 2, negative 1, 0, and this vector, 0, 2, negative 1, those would form an independent set that would be a basis for the span of S. All right, so I'll call this S prime. S prime, right, is equal to just these two vectors, 2, negative 1, 0, and the vector 0, 2, negative 1, right? I only need these two to form the same span as S does. All right, the span of this set is going to be equal to the span of this set. Right? And this is a basis for the span of S. All right, these are independent, these two. All right, and let's check. Let's see. Now the span of these 3 vectors, you might think, oh, there's 3 vectors. So the span of those 3 vectors should be, 3D space, all of R3. That's not the case, right? I said the span of 3 independent vectors was all of R3. What we've seen here is that the span of these 3 vectors is equivalent to the span of just these 2 independent vectors. And remember, the span of 2 independent vectors forms a plane, right? A 2-dimensional space. And you'll see that when I go to the GeoGebra site. All right, so that was the last example. All right, this example had 2, negative 1, 0. Go back to the home view, the standard view. All right. 2, negative 1, 0, that vector. 0, 2, negative 1. Again, it's kind of, you can't barely see it. There's a little dotted behind it there, a little green vector. And then 6, negative 5, 1, a blue vector. Can you see how they're all on the same plane? I can line them all up like that. All right. Or like, just kind of roll it this way. See how they're all pointing on, they're all on the same plane. I can line them all up nicely. It's not like the last example where when I line 2 of them up, the third one was clearly pointing in a different direction. And you see how they form a plane, right? The span of these 3 vectors would form this plane, this sheet, right? And hopefully it's clear that all 3 of these vectors, the green, the blue, and the red, are on this sheet, this pink sheet here. There, you can very clearly see it that way right there. They're all on the pink sheet. Okay, so the span of these 3 vectors, I don't need one of them, right? I can get rid of one of them and still get that same plane. So that's why I got rid of 6, negative 5, 1, because the span of these 2 vectors, the red and the green, would still be this same plane. Now I can't get rid of 2 of them, right? I can't get rid of this one because remember the span of one vector would be a line, not a plane going through the origin. So I need at least 2 of these around, right? So that's why I kept the first 2. and those first two, the 2, -1, 0, 0, 2, -1 is a basis for that plane, a basis for the span of S, which would make a plane. Okay. And I finally have one last example. Hooray. Very nice hour-and-a-half video. Cool. So last example, another example where I have a set of 3 vectors in R3. And the question is, there's 1, -1, 3, 3, -3, 9, -4, 4, -12. Now hopefully you can see that these 2 vectors are just scalar multiples of the first one. So what you're going to see in the end here is that I only need one of them. The span of this is going to be the same as the span of one vector, or just a straight line going through the origin. All right, well again, S spans the span of S. That's by definition. But like I said, you can already tell this is not an independent set. This vector is 3 times this one. So S is dependent, meaning that S is not a basis for the span of S, for that vector space. So let's find one, right? So remember, when I was checking for independence, setting a linear combination of these 3 equal to the 0 vector, I'd have this corresponding coefficient matrix, where each column is just a vector from S, and then bar, and then some zeros over here. And then I would put this into reduced row echelon form. And let me go to the calculator for that one more time. And turn it on. So again, over here to edit, enter a 3 by 3 matrix. First row is 1, 3, -4. Second row is -1. Obviously, the second row is -1 times the first row, and the third row is just 3 times the first row. So I can get rid of those last 2 rows. Actually, I don't know why I'm doing this, because the first row is going to stay the same, and these last 2 rows are going to be zeros. All right. Oh, I'm halfway there. Let's just finish it off. So -1, -3, 4, and then 3, 9, 12. And get out of here. Oh, enter. Oops, clear that. Sorry. 12 for that last entry. Get out of here. Entry. And yeah, just. Oop, did I enter something wrong? Go back. It's 1, 3, -4, -1, -3, 4, 3, 9, 12. Oh, I see. That should be -12, shouldn't it? I have -12 in the components up here, and I don't know why I did that. -12. This should be -12. Aha. Yeah. So, my apologies. Let me just go quickly over here, move the cursor down to that entry. -12. Wonderful. Alright, now the reduced row echelon form should have those 2 rows of zeros, as I mentioned. Great. Alright, so yeah, I didn't need to do that with the calculator, right? Like I said, I recognize that the second row is just -1 times the first row, and the third row is just 3 times the first row, right? So 1, 3, -4 sticks around, and then you eliminate these rows down here, make them 0 rows. So you see there's only one pivot column, so corresponding to this vector, right? So the set with just this vector, just 1, -1, 3, would be good enough, to be a basis for the span of S. So I'll say S prime equals, just the vector 1, -1, 3 is a basis for the span of S, right? Right, and the span of this set will be equal to the span of that set. Well, what was the span of one vector? Just a line, right? And we're going to see that here. So last example, got my last pictures up here. Now the S had this vector, this vector, 3, negative 3, 9, and this vector. And look at how they all fall on the same line. See that? All three of those vectors, green, red, and blue, are on the same line. And when I enter that line, there it is, it's a pink. They're all right on top of it. So I don't need two of these, right? The span of this vector forms a line. The span of these two vectors would form the same line because they're on the same line. The span of these three vectors would form that same line because they're all on the line. So again, I don't need two of them to form that same space. Right, I just need one vector. And again, you could have chosen one of the other two instead, but I just again had it corresponding to a pivot column. So 1, negative 1, 3 would be a basis for this vector space, right, which is the span of S. Wonderful. All right, so that's a lot of stuff. I know it's an hour and a half here. I did the same thing over and over again, right? You can just very quickly, if you're given a set of vectors and asked to find a basis for the span of that set of vectors, just use those vectors as a column in a matrix, right? Set up your coefficient matrix for the corresponding system if you were checking for dependence or checking for spanning. You'd have that same coefficient matrix. Put it in reduced row echelon form, or even just row echelon, or even just echelon form, row echelon form, because again, the pivot columns in echelon form will be the same as the pivot columns in reduced echelon form. So you can do either one. And then the pivot columns in the echelon form or reduced echelon form will correspond to vectors from S that will form a linearly independent set and therefore be a basis, and thus be a basis for the span of that set. All right, so again, you can just keep doing that over and over again. All right, so have fun practicing this kind of stuff, and thank you for watching.